Welcome to lecture 22, where we introduce a new language, the language of infinitesimals. Now, the language of infinitesimals is based on three symbols: the little o, the big O, and the asymptotic equivalence. Now, the little o, is fundamental for limits. The big O is not important now, but it will become important later. And the asymptotic equivalence is a related concept which, however, can become dangerous for limits. We will understand more about this later. But let me give the first definition. Definition 1. Let f be a function defined in D with values in R. Let x naught be an element of the extended real line, and G another function defined in D with values in R. We say that f of x is equal to small o of g of x for x that tends to x naught if there exists a function omega defined in D with values in R, so same domain and codomain of f and g, such that there will be two conditions, 1 and 2. First condition is that we can write f of x as omega of x times g of x for every x in the domain D. Second is that the limit of omega of x when x tends to x naught is equal to 0. Now, notice something. If f of x, or let's say if g of x tends to 0, then f of x tends to 0 more. So this is a first interpretation of this little o symbol. Okay, when we say that f of x is equal to small o of g of x, now we are saying that if g of x tends to 0 and f of x is equal to small o of g of x, this is just like saying that f of x tends to 0 faster. However, this is not always the case. Okay, this is not always the case. We'll come back on this later. This will become more clear later. For the time being, we have just a definition of what small o means. Okay, given a function f of x, given another function g of x, we can say that f of x is small o of g of x is if there exists a third function omega that satisfies these two conditions, 1 and 2. We give now an alternative definition of little o. Okay, so this is the definition 2 alternative. Now, again, we have f defined in D with values in R, x naught an element of the extended real line, g defined in D with values in R. But now there is another condition that we need to have. G of x will be different from 0 for all the x that belong to D except the point x naught. Okay, so we are saying that in the domain of definition D, except x naught, g of x will be different from 0. Then we can say that f of x is equal to small o of g of x for x that goes to x naught if the limit of f of x divided by g of x as x goes to x naught is equal to 0. Clearly, this second definition can only be applied where this fraction has a sense, has a meaning, and this fraction has a meaning only if g of x will be different from 0, okay, for all x's different from x naught. Okay, so let's now give the definition of asymptotic stability, which was the other concept relevant for us. So definition, again, the same setting. So we have f defined in D from D to R, x naught into the extended real line, g defined in D with values in R, and we say that f of x is asymptotic equivalent to g of x. So this symbol stands for asymptotic equivalence. If so when this happens, if there exists a third function omega from D to R such that, again, we have two conditions, 1 and 2. First is the same, f of x can be written as omega of x as g times g of x for every x in the domain D. And now the limit of omega of x when x goes to x naught is equal to 1. Okay? Alternative definition would be that, of course, with the same setting for f, x naught, and g, we say that if g of x is different from 0 for x different from x naught, then we say that f of x is asymptotically equivalent to g of x if the limit of f of x divided by g of x as x goes to x naught is equal to 1. Okay, so let's now see these definitions in the context of a few examples. Okay, let me start with the example 1. We say that x to the cube is equal to small o of x squared for x that tends to 0. And we recognize that in this case we have f, this is f of x, x to the cube. We see that x to the square represents g, so both these functions are defined on D, which is the entire real line. Now, to see that x to the cube is little o of x to the square, we need to find, okay, we need to find an third function omega from R to R such that, well, what are the two conditions? First condition is that x to the cube need to be written as omega of x times x to the square, and second, limit of omega of x when x goes to 0 is equal to 0. Okay, what can we do with the first one? We can rewrite x to the cube equal to something times x to the square, but clearly we see that x would do the job, right? So we can clearly say that omega of x is equal to x, and if we take the limit as x goes to 0 of x, we clearly get 0. So this proves that the initial statement is correct. We can say that x to the cube is equal to little o of x to the square for x that goes to 0. Let's see another example. Example 2. Let's take the function sine square of x, and we say that this function is small o of x for x that goes to 0. And now we are taking as the domain of the function the real line except the origin. Okay? Now, once again, we see that f is sine square of x, g is simply x, so we need to find another function omega such that sine square of x should be written, so this is f, and should be written by omega times what, x. But clearly, by just dividing and multiplying by x, we see that this function is sine square of x divided by x. Okay, so we have this function which is defined for all x that belongs to D. So the next condition is that we need to check is that the limit as x goes to 0 of sine square of x divided by x is equal to 0. But this is easy to check because the limit as x goes to 0 of this can be written as sine of x divided by x times x, and we see that this tends to 1, this tends to 0, so yes, this limit is indeed 0. Now, to prove that sine square of x is little o of x, we could also have used the definition 2. Because in fact we know that g of x, which is in this case x, is different from 0 for every x that is different from 0, right? So we can just say that to verify the first statement, we need to prove that the limit as x goes to 0 of f of x divided by g of x, which in this case is the limit as x goes to 0 of sine square of x divided by x, but we just proved that this limit is 0, and this would be sufficient to prove the statement. Okay? Right, so let's move now to a third example. Let's take the example 3. Example 3. So we have tangent square of x equal to small o of arc tangent of x for x that goes to 0. So in this case, f is just tangent square of x, g is arc tangent of x. Let's see if we can apply, or where we can apply the second definition to prove this. We need to check that g of x is different from 0, but remember that from the graph of the arc tangent of x, we know that the graph is this, right? So it is between minus pi over 2 and pi over 2, and this is the arc tangent of x. So if we define d as the real line except the origin, we can then certainly apply the second definition. So the only thing that we need to check at this point is that the limit as x goes to 0 of tangent square of x divided by arc tangent of x is equal to 0. How can we evaluate this limit? Well, we can write this as limit as x goes to 0 of, we can write this as tangent square of x, and we can divide by x squared, and then we have x divided by arc tangent of x, and then once again times x. And we immediately recognize the fundamental limits. This is 1, this is 1, this goes to 0. So this finally proves that this limit is equal to 0. Okay, so that was easy. Let's now give a final example. Example 4. 1 over x is equal to small o of 1 over sine square of x, okay, for x that goes to 0. And okay, so this is one of those examples where f, which in this case is 1 over x, and g, which is 1 over sine square of x, they do not tend to 0 when x goes to 0. Okay, so this is basically the justification of what we said before. Remember that right at the start we said that of course if g of x tends to 0 and f of x tends to 0, then we say that if f of x is small o of g of x, then it means that f of x tends to 0 faster, more. But it is also possible to define a little o without having these two functions that tends to 0. And this is exactly the situation where we are now. Because we have 1 over x, when x goes to 0, this will go to plus infinity. And also 1 over sine square of x, when x goes to 0, it will not tend to 0, but it will go to plus infinity. Still, we can define that f of x is little o of g of x. Okay, let's see how we can prove this. Well, we can write 1 of x equal to something that multiplies 1 over sine square of x. Well, but this something is clearly sine of sine square of x divided by x. So we immediately recognize that this is f, this is g, this must be omega. So we need to check now that the only thing that remains now to be checked is that the limit as x goes to 0 of omega, which is sine square of x divided by x, is equal to 0. But this is easy because this is just the limit as x goes to 0, sine of x divided by x all times sine of x. And we see that this tends to 1, this tends to 0, so yes, this limit is indeed equal to 0, which finally proves what we were looking for. Now that we have some familiarity with these ideas of little o, we start discussing some algebraic properties, which will be very useful for more complex application. Okay, so let me introduce the algebraic properties of small o of x. So let's suppose that we have a function f1 of x which is small o of g of x. Okay? And then we have another function f2 of x which is equal to small o of g of x, both for x that goes to x naught. So what we are saying is that we have now f1 which is little o of g of x, and we know what that means, right? It will satisfy all the previous condition. The same is true also for f2 of x, and we want to see now what happens if we take the sum difference of these two functions f1 f2. Let me start with the sum difference. So let me consider f1 of x plus or minus f2 of x. And I'm saying that this f1 plus or minus f2 is still little o of g of x for x that goes to x0. And let me prove this. Why is that? Well, thing is that if we just take the definition of f1 of x to be equal to little o of g of x, well, this implies that there exists a function of omega 1 of x such that, well, the two conditions are that f1 of x is equal to omega 1 of x times g of x, right, for in the domain of definition of the function. And we also have that the limit of omega 1 of x when x goes to x naught is equal to 0. Now we can repeat these for the function f2, right? I'll just copy this and we'll just change this 1 into 2 because this is exactly what happens, right? So we have that f2 of x is equal to little o of g of x if there exists an omega 2 of x such that f2 of x is equal to some omega 2 of x g of x, and the limit of omega 2 of x is still equal to 0. Now this implies that if we take f1 of x plus or minus f2 of x, well, by just using the previous conditions, we see that this is equal to omega 1 of x times g of x plus or minus omega 2 of x times g2 of x, right? Which is equal to omega 1 of x plus or minus omega 2 of x, all this multiplied by g of x. Sorry, this is just g of x. But we can now call this, omega of x. So we just proved at this point that f1 of x plus or minus f2 of x is equal to omega of x times g of x, with omega of x that tends to 0 when x, we can write this, which proves the original statement that the sum difference of f1 and f2 is just another example of little o of g of x. A very similar proof can be given for the case of the product. So let's consider now, the product. So again, with the same hypothesis that f1 is little o of g, f2 is little o of g, we would like to explore now what happens f1 of x times f2 of x. And it turns out that this is little o of g squared of x. Now, of course, for x that goes to x naught. Now, let me prove this statement. We have that f1 of x times f2 of x is equal to omega 1 of x g of x times omega 2 of x g of x. But this is omega 1 of x times omega 2 of x times g squared of x. And if we call this omega of x, well, it is easy to see now that limit of omega of x when x goes to x naught is again equal to 0. So this finally proves the two conditions are satisfied, and we know now that the product of f1 and f2 is little o of g squared of x. What about the multiple? If we multiply, so let's consider the multiple of a function. So let me consider alpha f1 of x, okay, where alpha is any real number. So somehow this is a multiple of the function f1 of x, and I'm saying that this is small o of g of x. And I'm not saying for x that goes to x naught. Of course, all these statements are valid for x that goes to x naught. How can we prove this? Well, alpha f1 of x is equal to alpha omega 1 of x times g of x. And we have now this that we can call omega of x. So clearly, once again, we can write this as omega of x times g of x. So first condition satisfied. Second condition, we need to prove that the limit of omega of x as x goes to x naught is equal to 0. But this is just the limit as x goes to x naught of alpha, which is just a constant, time omega 1 of x, and this is clearly equal to 0. So this concludes the proof. Now, one last thing that would be interesting to see is if we can do something about the ratio of f1 and f2. So what about f1 of x divided by f2 of x? Can we conclude something about the infinitesimal relationship with g of x? Well, if we take this ratio, let's suppose that we write this f1 of x divided by f2 of x by just replacing the expression that we have from the definition. So we have omega 1 of x times g of x, then we have omega 2 of x times g of x. Well, clearly the 2g of x they will cancel. So this will cancel with this, but now we have an undetermined form, right? Because in this case we have 0 over 0, which we don't know a priori. Okay, so we cannot take any conclusion about this. So I will write this in red, no conclusion. We can summarize all what we have seen so far as follows. Summary. Okay, we can say that if we have little o of g, okay, a function which is a little o of g, plus or minus another function which is little o of g, this will return a function which is little o of g. Then we said that if we have little o of g times another little o of g, we get little o of g squared. Then we saw also that if we have a little o of alpha, or let's say if we have alpha times little o of g, well, we know that this is little o of g once again. And unfortunately, we cannot say anything about little o of g divided by little o of g. This will remain unexplored. Okay, so this is what we have. These are the results that we found so far. Let's make another attempt now, and let's try to explore the possibility that f of x, a given function f of x, okay, is a small o of alpha g of x. This is something that we did not explore, right? So this is just like saying that we are given a function f of x, okay, and we are saying that this is a little o, not of g of x, but just of the multiple of g of x. Now, this implies that first, f of x, the first condition is that f of x can be written as some omega of x times alpha g of x. But once again, we recognize that this first part, well, we can think of this as a new omega 1 of x. So we can rewrite this as omega 1 of x times g of x. Now, if we manage to show that omega 1 of x tends to 0, we're done, right? So we need to prove that, but clearly omega 1 of x, which is just alpha, a constant, times omega of x, this will tend to 0 for x that goes to x naught. So yes, we can definitely say that in general, another conclusion is that if we have small o, little o of alpha g, we can definitely say that this is little o of g. Okay, so this is another thing that it is worth remembering. Another interesting property we would like to explore is that of transitivity. So let's suppose that f of x is equal to little o of g of x, and g of x is little o of h of x for x that goes to x naught, then we can conclude that f of x is equal to little o of h of x for x that goes to x naught. In other words, little o is transitive. Let's prove this. Now, if we rewrite the first hypothesis, f of x equal to little o of g of x in terms of the omega function, well, that means that there exists an omega 1 of x such that f of x can be written as omega 1 times g of x. But at the same time, we can now replace the second hypothesis on g of x, which implies that there exists another function, omega 2 of x, such that g of x is omega 2 of x times h of x. And we have now this product, which we can call omega of x. So we can now say that f of x is omega of x times h of x. The only thing that needs to be verified is that now omega of x, which is omega 1 of x times omega 2 of x, will tend to 0. But this is clear because we know that this will tend to 0 and this will tend to 0. And this will conclude the proof. Right, so let's now explore another aspect related with the infinitesimal, which is that of composition. Let's do compositions of functions, okay? So if f of x is little o of x for x that goes to 0, then with this, let's see what happens if we would like to evaluate the function f not in x but in the arc tangent of x. So what we are doing is basically a composition of two functions, f of x and arc tangent of x. We are taking arc tangent of x as the argument of the function f of x. And we would like to prove now that if we do this, the new function that we obtain is again little o of x for x that goes to 0. Let's prove this. We can write f of x, because f of x is little o of x, we can write this as omega of x times x. Now, if we replace x with arc tangent of x, we have that f of arc tangent of x is equal to omega of arc tangent of x times arc tangent of x. So far we have just replaced x with arc tangent of x. But now we can rewrite this as omega of arc tangent of x times arc tangent of x divided by x times x. This is exactly the same thing, right? And we see now that these two terms, okay, let me call this omega 1 of x. Now we have that f of arc tangent of x has been expressed as the product of omega 1 of x times x. Now the last thing we need to prove is that the limit as x goes to 0 of omega 1 of x, which is omega of arc tangent of x times arc tangent of x divided by x, we need to prove that this limit is equal to 0. let's see what we get. Well, from clearly the first one, we know that when x goes to 0, arctangent of x goes to 0. And that implies that omega of arctangent of x goes to 0 as well. Instead, this is a fundamental limit. We know that this will tend to 1. As a final result, we get that this is equal to 0, which proves basically that f of arctangent of x is indeed equal to little o of x. Okay, let's attempt now a new composition. Okay, composition 2. Let's do the opposite. Let's take the arctangent of f of x. Okay, so we are now using f of x as the argument of the arctangent. And remember that the first hypothesis still holds. Okay, we are always assuming that f of x is again little o of x. Okay, and we want to prove now that this new function that we just have obtained is equal to little o of x for x that goes to 0. Okay, now if we have we know that f of x is equal to little o of x, so that implies that f of x can be written as omega of x times x. Okay, where omega of x of course is something that will tend to 0. But this implies that arctangent of f of x, right? So this can be written as, let me change the color because this is just a proof. So I'll make this blue, right? And let me change the color of the pen. So we want to prove now arctangent of f of x. Okay, so we can rewrite this as follows. Arctangent of f of x divided by f of x. Then we again write f of x divided by x, and then we multiply by x. Why am I doing this? Because remember that we would like to prove that arctangent of f of x is equal to little o of x. So I've just re-expressed this as a product of this function, which for me is going to play the role of a new omega 1 of x times x. So the last thing we need to prove at this point is that the limit as x goes to 0 of arctangent of f of x divided by f of x times f of x divided by x, this needs to be equal to 0. Let's see if this is the case. Well, we know that this limit, when x goes to 0, we know that f of x goes to 0. So this is again another example of the fundamental limit, and this will tend to 1. Not only this, we know that f of x is little o of x, so this clearly will tend to 0, which proves that the limit of omega 1 of x is indeed equal to 0. So we have also this other part proved. Okay? Now let's see if we can apply all these ideas to some example. Okay, so let me start with this example. What I would like to prove here is that sine of 2x is asymptotically equivalent to 2x for x that goes to 0. Right, so remember the definition of asymptotic equivalence. Let me go back to this definition right at the start. What we said is that f is asymptotically equivalent to g if we find a third function omega such that f of x can be expressed as the product of omega times g, and this omega has to be a function that tends to 1 when x goes to x naught. Okay, so in our situation we have, for our example, we have that f of x, of course, is this sine of 2x, right? So this is instead g of x, okay? So we would like to express f of x as omega of x times g of x. Now, this is not difficult because we can write sine of 2x. We just divide and multiply by 2x, so we can write sine of 2x divided by 2x times 2x, and this is the new omega of x. We need proof now that omega of x is a function that tends to 1, but that's easy because the limit of when x goes to 0 of omega of x is the limit as x goes to 0 of sine of 2x divided by 2x, and we remember by a simple change of variable y equal to 2x, clearly we see that this is equal to 1. So yes, we finally have that we can say that sine of 2x is asymptotically equivalent to 2x. Let's consider another example of asymptotic equivalence. Example 2. Let's consider this: e to the x minus cosine of x is asymptotically equivalent to x for x that goes to 0. Now, same story. We see that this is f of x, this is g of x. Well, we need to find omega of x such that f can be expressed as omega times g with the omega that tends to 1. Now, we need now to play a little bit with what we know about fundamental limits, and we immediately recognize that e to the x minus cosine of x can be written as e to the x minus 1 plus 1 minus cosine of x, which again can be written as e to the x minus 1 divided by x times x plus 1 minus cosine of x divided by x squared times x squared. And we did just this because we recognize now that, sorry, this is x to the square, okay? And we see here that we can rewrite this as e to the x minus 1 divided by x. I will be factoring out 1x here, plus 1 minus cosine of x divided by x to the square times x, all this multiplied by x. And you see why I'm doing this, because this is my g, right? This is my g, so this must be my omega of x. So we need to prove now that the limit as x goes to 0 of omega of x is equal to 1. Okay? Is this equal to 1? Well, let's see. The limit as x goes to 0 of e to the x minus 1 divided by x plus 1 minus cosine of x divided by x to the square times x. Now what do we have? Well, we have that this tends to 1. This tends to 1/2, but this tends to 0. So clearly this limit is equal to 1, which is exactly what we wanted to prove. All right. Another example of asymptotic equivalence. Example 3. Let's suppose this is more general kind of results. So let's suppose that f of x is little o of g of x for x that goes to x naught. Okay, and then let's say that g of x is asymptotically equivalent to another function h of x, always for x that tends to x naught. We would like to conclude that f of x now is also little o of h of x. Okay, let's prove this result. This is quite intuitive, right? But we need to make a proof. So we know that f of x is equal to some omega x g of x, right? Yep. So we also know that with omega of x, let me call this omega 1, okay? With omega 1 of x that goes to 0 when x goes to x naught. Then we have that g of x is equal to some omega 2 of x times h of x with omega 2 that of x that tends to 1 when x tends to x naught. So we can write that f of x is equal to omega 1 of x times omega 2 of x times h of x. And if we consider this as the new omega of x, we can write f of x as omega of x times h of x. But now we need to prove that omega of x tends to 0. But this is clear because omega 1, this will tend to 0. This will tend to 1, so the product is going to tend to 0. So that was easy to prove, right? And a similar result is the following. Let's consider now f of x as little o of g of x for x that tends to x naught. And now we have that f of x is asymptotically equivalent to f of x for the same x that tends to x naught. Then we would like to conclude from these two that, f of x is asymptotically equivalent to some, let's say, h of x. We would like to conclude that h of x is equal to little o of g of x. And the proof now is very similar, because once again we can say that f of x is equal to some omega x g of x with omega that tends to 0. Then we say that h of x is equal to omega 1 of x f of x with omega 1 that goes to 0. And from this it follows that h of x is equal to omega 1 of x times f of x, which is omega of x times g of x. And if we call this omega 2 of x, we can say that h of x is equal to omega 2 of x g of x, with omega 2 of x being omega 1 of x times omega of x, and this is clearly something that will tend to 0. Why? Because we know that omega tends to 0. Omega